Okay, so here's my video for solving step 8. So we've got some formulas. Force equals mass times acceleration. Force due to drag is 1/2 CPA V squared. Well, I'm assuming my density of my liquid / air is 1.175. Sorry about that. So, blowing stuff off my camera. So we set plus this should equal 0, so we're gonna say that the acceleration is negative and this is positive, but anyways, combined they'll equal 0. And so we set this over on the other side, negative m dv dt, since acceleration is dv dt. Then so we set b equal to 1/2 CPA, so 1/2 CPA, so we don't have to write that every single time. bv squared, negative m dvt, so we do some differential equations. This is equal to 1/v, so we flip this. Oh, that's the next step. Then we flip it. So we get our v equal to m over 1/2 CPA times, well, RT here on the end. So to solve for t, we equal t equals 2m CP, or well, density AV. So since I didn't really know the coefficient of drag for these, I just took your data and solved for the coefficient of drag. So I took 2 times your force that you provided times my density times my area times my velocity squared. I took the top velocity for each of these. Clicked on the wrong thing. So I took the 7.2 velocity as my baseline to calculate my coefficient of drag, coefficient of friction, whatever coefficient you want to say it is. In this scenario, it's drag. So I used that to solve for my coefficients of each. You know, this is a sphere, this is a sphere diameter for the golf ball. And then this is 1.38, 1.95, depending on the direction you've thrown it. And I just did it based off the areas that I did here. I'm not sure if that's actually accurate because my coefficient, this is large, block small, and obviously the drag coefficient is higher on the large. Well, I guess that's accurate. It's a lot bigger. So it looks like I have drag coefficients that seem appropriate, 0.79, 0.77. That's somewhat okay. I can't remember what a sphere is supposed to be. I think it's 0.7 is what it's supposed to be, so they're somewhat close. So using that drag coefficient calculated individually from data provided experimentally, I found each drag coefficient. And because now I have the drag coefficient, I use that to solve for velocity. It gives me, well, this is a terminal velocity. And it gives me a baseline for my velocity at terminal velocity. So using my provided velocity, now that I've got it here, I can solve for my time in this here. Because the integral involved time, but you know, if I didn't know the velocity and I didn't know time, then I'm screwed. So we set up knowing the terminal velocity, which is what we're solving for here. Really, it just depends on the time. So we're just setting it up so we can find the one thing. So that's my equation for solving time. ds dt, so my position, this is velocity. Oh, low battery. ds dt, m over bt. Integral of ds equals yada yada. We pull the m and b out, 1/t, that's an ln. So we don't really need to do e to the any power, so s equals this. This is my position formula. And we can rewrite this so that it's a little more organized. 2 ln of t times m divided by CPA. So then we get our formulas for 50%, 90%, 99% of velocity. So we take our terminal velocity, oh, I'm missing it here. you can see that I did it. Anyways, so since there's a 1/2 on this side, this is timesing everything. This isn't on the bottom. This isn't denominator. Otherwise we would have an issue. Anyways, half of this will equal the velocity I'm just trying to find. So the first time I tried to do this on this side, and obviously it gave me double the time and kept screwing everything up. And then I had also done the integral wrong over here, and that kept messing me up for position. So hopefully this is all accurate now. So that gives me the actual velocity at half. So now I've got the half velocity. I can put that in my equation here to solve for time. And since I've got time, now I can solve for position. And I do that on each one of these, and this one's times 0.9 because we want to do 90%. And this is 0.99 because we want 99%. And we do that on each scenario. And so since this is 0.99 or whatever, you just do 18.8 over 10, and this is 18 over 10, since it's really a 9 over 10, and this is 9.9 over 10. And since there's a 2 times in the front, they just double. And so once we solve for t, then we can just put in the t value instead of carrying through all this junk. I guess that might have been useful, because if I'm doing this times that divided by that, common denominator, maybe we could have canceled some stuff. But anyways, that's what I used for these formulas. Now I plugged it into handy dandy Excel, and you can see my terminal velocities here: 801, 4239, 81, 2,880, 272, which seems like that's a freaking way long distance, but I don't know. That doesn't quite seem right. You know, it does seem right for time and maybe speed. That's pretty freaking fast. But that's what the values came out as. So velocities for my terminal velocities on each of those, and this is my 50%. And there's my 90%. I noticed that V and T are pretty linear in differences. But position was not. Obviously it's logarithmic according to my formula, so. And it sort of makes sense, because your acceleration is going to be constant. Well, acceleration and deceleration is pretty close to constant. I would assume that's why we were able to create a coefficient. I mean, we're assuming it's sort of linear. That's definitely an assumption, because of they mentioned it and you said to not worry about it. But so those are my values based off of the mass, density of the air, the area. Originally, I was going to match the force, but I don't think that was actually necessary in the end. Based off the formulas I used. Because we just converted this over. And we integrated the mass into this side of the formula, and then we did everything here. Integrated. I meant not as in integral, but like involved this. That's funny. So that's that. I'm not sure if I did any of it. You know, maybe some of my values were wrong somewhere. You know, in Excel that just carries over and over and over and over. But in essence, they seem to be somewhat right. I'm just not sure my velocities and my positions, if that's actually an accurate value, but I think all my formulas are accurate. Maybe I just messed up somewhere in some earlier calculation. It'd be interesting to know what the right calculation was. And you know, these are all coefficients of friction based off of assumptions, so that might be a factor. But there's terminal velocity, 50%, 90%, 99%. These are all, like I said, there's Excel formulas for each of these. Oops. I mean, that's, never mind. That one's a stupid one to list. What the heck? Escape. Okay, so you can see those formulas. And then this one is position formula. You can see there's an ln of this inside there, blah, blah, blah. So that's all calculated out, and that's what I get. But really, it's in the formulas here, and I think these are accurate. Hopefully they are. I mean, I did the differential equation, so maybe they're not right. And this is just based off of the idea that we're basing it off of half of whatever our velocity was at terminal velocity, so I half this side. And that should give us a value for t, since we know all these other things, and so t will equal this. And so our next step would be to put our t inside our position function, and that should give you an accurate position, but maybe that's not right. Hopefully it's right. Thanks. Let's see. Oh, terminal velocity, 50, 90, 50, 90, video submission. Yeah, if objects do the following. Well, these are definitely a significant height. I mean, well, I guess these are in meters, but that's still really high. 288 kilometers, 307 kilometers, 120 kilometers, 175 kilometers, 747 or 774 kilometers. That seems ridiculously high. So I don't know that these are actually correct. But that's the number I'm getting, so I did it off velocity squared. My velocity squared over here, and I mean, I was consistent with that. I didn't mix that up, you know, because sometimes they get rid of the squared and just do a coefficient without velocity squared. And I'm suspicious this is not accurate, but this is what I'm getting. So maybe I did it wrong. I'm not the best at differential equations. I mean, I'm taking the class right now. We'll see. I guess I should also note that when I calculated my drag force, I mean, there's an option where if it was something simple, you know, like it says here, when a body slides across the surface, frictional force is approximately constant and given by motion friction times newtons. I'm not sure why they have newtons there. Normal force, excuse me. It could be newtons. Unfortunately, frictional force on a body moving through a liquid or a gas does not behave so simply. The drag force is generally a complicated function of the body's velocity. However, for a body moving in a straight line at moderate speeds through a liquid such as water, the frictional force can often be approximated by friction force negative BV. So, I didn't use Reynolds number or anything fancy like that, and I didn't do a baseline based off of my, where the heck did my mouse go? I could have, inserted a function, a linear function approximation here, which I didn't. That might have been more useful to approximate just the way they did here, and get an e to the power for your velocity and find your position this way. But I tried to do it the different route where I found the coefficient of friction, or excuse me, coefficient of drag, and so that I had an accurate, even though it's probably less accurate. And so when I did my differential equation, it ends up as 1 over v squared instead of 1 over v, which gets you the ln, and then you cancel that out. Because I didn't need to get rid of anything to find the actual value for velocity. So I think my formula is accurate if I were doing it a certain way, but I don't know that doing it a certain way was right, because I probably just got the wrong coefficient of friction. Now, like I said, these coefficient of frictions aren't the greatest, and 0.7 is on the high end for a golf ball, or what, 0.77. But it might explain some of the weird numbers I've gotten over here. So I'm not sure that I did this right, but I sure gave a hard try. If that counts for anything. I'd love to be shown how to do this correctly and what my thinking was wrong. I think I had right thinking, but I need to record some of the discussions I've been talking about. This is Gavin, Justin, Gavin, me, Gavin, Justin. These are our discussions, and they did it a little bit different. They did a linear coefficient of friction. I'm like, I keep saying coefficient of friction. Anyways, the way they set it up, they have a linear coefficient of friction times your velocity equals my negative mg for them. Now, from what I understand, that wouldn't be entirely accurate, because that's an oversimplification what's going on here, but mine isn't right because I'm not doing the Reynolds number, accounting for the Reynolds number. So I think they did it right with what you wanted, but I don't know where all this information is. I kept looking for information and guidance on what you want, but I pull up the assignment and that's all I've got. So I've looked at the old stuff, but anyways, I'm at a loss really. So if you can correct us, that'd be great.